We have learned so much about motion in last chapter and previous chapters, and in this chapter we will talk about statics, which is the study of forces in equilibrium. This is a large group of situations that make up a special case of Newton's second law. There are actually two conditions that must be satisfied to achieve equilibrium. The first condition necessary to achieve equilibrium is the one already mentioned. The net external force on the system must be zero. Note that if net force is zero, that means the net external force in any direction is zero. So we have net F sub x and net F sub y both equal to zero. This condition applies to both static equilibrium, where the object is motionless, or dynamic equilibrium, where the object is moving at a constant velocity. However, it is not sufficient for the net external force of a system to be zero for a system to be in equilibrium. In these two pictures, the ice hockey stick lying flat on ice. Friction is negligible, and the gravitational force is balanced by the normal force from the ice. If we only consider the horizontal direction, we have in both cases the net external force is zero. However, only in the first case equilibrium is achieved, and the stick remains motionless. In the second case, the stick experiences accelerated rotation, so that we know, besides the condition that the net external force is zero, the point at which the force applies is another factor in determining whether or not equilibrium is achieved. The second condition necessary to achieve equilibrium involves avoiding accelerated rotation or maintaining a constant angular velocity. A rotating body or system can be in equilibrium if its rate of rotation is constant and remains unchanged by the forces acting on it. And this depends on a physical quantity called torque. Torque is a measure of the effectiveness of a force in changing or accelerating a rotation. It is the rotational equivalent of a force. In equation form, the magnitude of torque is defined to be Rf sine theta, where tau is the symbol for torque, r is the distance from the pivot point to the point where the force is applied. F is the magnitude of the force, and theta is the angle between the force and the vector directed from the point to the pivot point. Or if we define the perpendicular level arm, R perpendicular, as R sine theta, then the torque can be written as R perpendicular times force. The perpendicular level arm R perpendicular is the shortest distance from the pivot point to the line along which the force acts. The SI unit of torque is Newton times meter, usually written as N times M. The torque is always calculated with reference to some chosen pivot point, such as these nails. For the same applied force, a different choice of the location of the pivot point will give you a different value of the torque, since both the r and theta depend on the location of the pivot. Note that for rotation in a plane, torque has only two possible directions. Torque is either clockwise or counterclockwise relative to the chosen pivot point. The second condition necessary to achieve equilibrium is that the net external torque on a system must be zero. You can choose the point around which the torque is calculated, but it must be the same point for all torques. If the net external torque on a system is zero for one choice of pivot point, it will also hold true for any other choice of pivot point, if the system is an inertial frame of reference. Torques, which are in opposite directions, are assigned opposite signs. A common convention is to call counterclockwise torques positive and clockwise torques negative. When two children balance a seesaw, they satisfy the two conditions for equilibrium. Most people have perfect intuition about seesaws, knowing that the lighter child must sit further from the pivot, and that a heavier child can keep a lighter one off the ground indefinitely. Let's look at this example together. We know that for a balanced seesaw, both conditions of equilibrium must be satisfied, so that we have net force equals to 0 and net torque equals to 0. In part 1, since the F pivot is exerted on the pivot point, its lever arm is 0 and its torque is 0. Because the common convention is to call counterclockwise torque positive and clockwise torque negative, we have the net torque equals to R1 times W1, which is positive, minus R2 times W2 equals to 0. So that R2 equals to 1.30 meter. This result makes common sense because the heavier child must sit closer to the pivot to balance the seesaw. It is interesting to note that although the weight of each child is distributed over an area of the seesaw, we treat the weights as if each force were exerted on a single point. And the distance R1 and R2 are the distance to the points directly below the center of gravity of each child. In part B, to get the force F pivot, we use the first condition of equilibrium. In the vertical direction, if we define the upward as the positive direction, we have the net F force in the vertical direction equals to 0 equals to F pivot minus the weight 1 minus weight 2, so that F pivot equals to weight 1 plus weight 2 equals to 568 Newton. Even if a system is in equilibrium, it may or may not be stable. There are three types of equilibrium: stable, unstable, and neutral. A system is said to be in stable equilibrium if, when displaced from equilibrium, it experiences a net force or torque in a direction opposite to the direction of the displacement. For example, a marble at the bottom of a bowl will experience a restoring force when displaced from the equilibrium point. This force moves it back toward the equilibrium position. Most systems are in stable equilibrium, especially for small displacement. A system is in unstable equilibrium if, when displaced, the system experiences a net force or torque in the same direction as the displacement from equilibrium. For example, a marble resting on top of a hill, once displaced, will accelerate it away from the crest. If we use a pencil as the example, in this first picture on the left, the pencil is in stable equilibrium. CG here represents center of gravity. If the pencil is displaced slightly to the side, it is no longer in equilibrium, but its weight produces a clockwise torque that returns the pencil to its equilibrium position. If the pencil is displaced even further, the torque caused by its weight changes directions to counterclockwise and causes the displacement to increase. In this picture on the right, the pencil standing on its tip is in unstable equilibrium, although both conditions of equilibrium are satisfied. If the pencil is displaced even slightly, a torque is created by its weight that is in the same direction as displacement, causing displacement to increase. A system is in neutral equilibrium if its equilibrium is independent of displacement from its original position. One example is the marble on a flat horizontal surface. When we consider how far a system in stable equilibrium can be displaced before it becomes unstable, we find that some systems is more stable than others. The critical point is reached when the center of gravity is no longer above the base of support. The center of gravity of an L dot is above the hip joints and lies between two narrowly separated feet. In this figure on the left, the person is in standing position and is in stable equilibrium in relation to sideways displacement, but relatively small displacement can take his center of gravity outside the base of support and make him unstable. Besides, humans are less stable relative to forward and backward displacement because the feet is not very long. When bending in the manner shown, stability is increased by lowering the center of gravity. Stability is also increased if the base is expanded by placing the feet further apart. On the other hand, animals such as chickens have easier systems to control. The center of gravity of a chicken is below the hip joints and lies above a broad base of support formed by widely separated and notched feet. Therefore, the chicken is stable for front-to-back displacement as well as side-to-side displacement. Engineers and architects strive to achieve extremely stable equilibriums for buildings and other systems that must withstand wind, earthquake, or other forces that displace them from equilibrium. Although the examples in this section emphasize gravitational forces, the basic conditions for equilibrium are the same for all types of forces.